Estimating the time since the Big Bang, the age of our universe, a topic long debated, holds significant secrets about life and Earth's origins. A recent study challenges the widely accepted 13.8 billion years, suggesting our universe could be much older, 26.7 billion years or more. This revelation stems from research by University of Ottawa physicist Rajendra Gupta, who incorporates a 1929 theory by Swiss astronomer Fritz Zwicki. Zwicki's theory proposes that photons lose energy over vast distances, influencing the redshift data, and Gupta contends this aligns with an expanding universe. This reinterpretation of redshift as a hybrid phenomenon could resolve cosmological puzzles discovered by NASA's James Webb Space Telescope. Methuselah, a star 1,445 billion years old, poses a cosmic mystery, as it predates the universe's supposed 13.8 billion years. Astronomer Howard Bond notes this discrepancy, and the James Webb Telescope continues to unveil anomalies in distant galaxies formed earlier than predicted. This challenges the standard cosmological timeline, raising questions about our understanding of the universe's evolution. Webb's unexpected findings suggest stars and galaxies formed more rapidly than anticipated, challenging existing models. Pramodha Natarajan, a theoretical astrophysicist, suggests revisiting fundamental assumptions about galactic evolution to address emerging tensions. Resolving these tensions may lead to new ideas at the forefront of our cosmic understanding. Large groups of stars, as explained by Gillingworth, an astronomer at the University of California, Santa Cruz during a NASA press conference, raise intriguing questions about our understanding of early galaxy formation. We're left wondering if we truly grasp the initial phases of these galaxies. One prominent puzzle, highlighted, revolves around the role of dark matter in guiding the emergence of galaxies. Jorge P. Ruya, a cosmologist at the University of Edinburgh, simplifies the issue by stating that dark matter, unlike normal matter, doesn't interact through electromagnetic forces, but solely through gravity. We delve into the immediate aftermath of the Big Bang, where gravity started pulling dark matter into clumps known as halos. These halos acted as gravitational sinks, seeding the formation of galaxies in the early universe. The telltale motions of stars around still betray the endurance of these halos. However, James Webb's rapid discovery of early galaxies challenges our understanding. It prompts us to reconsider if these halos reached an immense bulk earlier than expected, raising questions about the very nature of dark matter. Around, we explore different theoretical treatments of dark matter, contemplating its potential interactions. The possibility of dark matter interacting with itself, possibly through an unknown force or particle not in the current standard model of physics, might explain the speed at which these halos grew. Ruya suggests that studying our galaxy's star formation today, roughly one new star per year, might help us understand how stars formed in dark matter halos early on. Castellano's paper proposes star formation rates 20 times higher in candidate galaxies, challenging our assumptions. Yet, cosmologist Michael Bowen-Colchin around cautions that such high rates stretch the boundaries of what is physically possible. This cosmic puzzle is likened to flipping through an old photo album and unexpectedly finding a full-grown adult instead of baby pictures. Concluding the script, Rajendra Gupta's study offers a fresh perspective, suggesting that understanding the age of early galaxies involves grappling with the age of the universe itself. One to the intriguing mystery that has puzzled scientists for ages, the enigma surrounding ancient galaxies. Recent studies by Gupta propose a groundbreaking revelation: the universe may be closer to 26.7 billion years old, almost double the previous estimates. This newfound perspective, as described by Gupta's innovative model, extends the timeline for galaxy formation by several billion years. This, in turn, opens up the possibility for the existence of seemingly impossible massive early galaxies, challenging conventional wisdom. Gupta emphasizes that the discrepancy in estimates stems from our limited understanding of stretched light waves. As the universe expands, light waves stretch, making it increasingly challenging to precisely measure the amount of light reaching us from the distant corners of an ever-growing cosmos. As we peer deeper into the vastness of the universe, we're essentially gazing back in time. The farther we look, the further back in time we glimpse, capturing fleeting snapshots of the past. This temporal journey is due to the time it takes for light to traverse the expansive void of space. Some scientific models liken this process to a spring stretching and pulling